Good morning to all of you. Today I will talk about the Poisson Sum Formula, and I will also introduce the topic on Markov chains. Right. So let's start with the topic, which is Poisson Sum Formula. Now, this is the I have straightway written down the formula, and the formula says that this is the summation of a function because the sigma is there, and this is some function, and its argument is n. N varies from minus infinity to plus infinity. So the summation of a function is actually equal to the summation over its Fourier transform. Sum from n equal to minus infinity to n equal to plus n plus infinity, n equal to plus infinity of some function fn is equal to a sum from n equal to minus infinity to n equal to plus infinity of the Fourier transform of that function. Now, I'm not very sure whether you have done the Fourier transform or not, because the Fourier transform actually comes in the subject of signals and systems. I don't remember the scheme of second year. But anyway, I will not go into the details of the Fourier transform. Fourier transform, when you take the Fourier transform of a function, what happens of a function or a signal? What happens is you take the Fourier transform of a signal, you will be able to know what frequency components are present in the signal. That means you are basically trying to do the frequency analysis of the signal, right? Once you draw the spectrum, you will be able to know what are the dominant frequencies and what are subdued frequencies. So that's the Fourier transform. Let's not let's not talk about the Fourier transform more, because that's a different topic. But what I will do is that there are various conventions of Fourier transform. The convention that we use, we have to prove this formula actually. This formula says the summation of the function is equal to the summation of its Fourier transform, right? When n goes from minus infinity to plus infinity. There are various conventions of Fourier transform, but what convention we will use here for the Fourier transform is depicted here. The convention that we use for Fourier transform is that the Fourier transform of some function fx, right, is equal to f cap k, right? It's the cap. So f cap k, and what is f cap k? F cap k, this capital F, it denotes the Fourier transform, and this is the function fx. Now, this on the left-hand side of the denotation is actually telling us the Fourier transform of this function fx. And this is also denoted by f cap k. All right, I've just changed the index. You will come to know in signals and systems, actually, there are two indices required. One is n and one is k. N actually tells you about the time samples, and k tells you about the frequency samples. But again, I'm saying that I'm not going into those issues, but you have to, but I will try to give you the mathematical formula so that you can, at least you can understand the maths behind this proof. So this says that the Fourier transform of this function fx, and this is also denoted by f cap k, and this is given by integral from minus infinity to infinity of this function into e to the power minus I, which is iota, 2 pi x k. Right, k is some index dx. So this integral the index here is the k going from minus infinity to infinity. That's why k is there. Or you can take n also, right? In general, when we talk about the Fourier transform, we define two indices. One is n and k. But here I will try to prove it using n formula. So I can rewrite this convention as because this is the Fourier transform. This formula is this equation tells you about the Fourier transform, and this is equal to f cap k. This is the general formula given. This is the formula of Fourier transform. You take the formula as such. the Fourier transform of a function is given by fx e to the power minus 2 pi xk, where k goes from minus infinity to infinity of dx. Now here in the actual formula, Poisson sum formula, this says that this is the Fourier transform with index n. So therefore, when I put the formula of the Fourier transform here, what I will get is, I will get the sigma will remain as it is, n going from minus infinity to plus infinity. I will use this formula here. N goes from minus infinity to infinity because here I am taking n as the index of the argument, n as the index. So fx e to the power minus 2 pi xn, this is n. Here it was k because here the argument of the Fourier transform function was k. But here I'm taking n. So fx e to the power minus 2 pi xn dx, right? So this is how I can write. I'm starting from the right hand side and I will prove it equal to the left hand side. Hence, the Poisson summation formula will be proved. And what is the Poisson sum formula tell us? It tells us that the summation of a function over n equal to minus infinity to infinity, the function is fn, is equal to the summation over summation of its Fourier transform from n equal to minus infinity to infinity. But that's a very, actually it is a very shocking result. Probably when you will study the signals and systems, then you will, realize the importance of the importance. I should call it as a shocking result, because summation of a function and you take its Fourier transform, they are equal. This is a new kind of result which this Poisson summation formula tells us. And I have started with the defining the Fourier transform. I'm using the Fourier transform in the right hand side equation. So I come up to this point. Next step is interchanging the sum and integral. We interchange the summation and the integral. We can do it mathematically, there is no problem. So I can take fx out because I have to interchange the integral, right? I can do it like this, fx, I can just manipulate the placement of the terms. Fx, then I take the summation inside and going from minus infinity to plus infinity, e to the power minus 2 pi I n x dx. Right. Then we know about this, the solution of this integral, e to the power minus 2 pi, e to the power minus I, e to the power I pi x, right? This we know that this can be, actually this is the summation of the delta functions. This I'm using the formula directly, but we can prove the formula also, there is no issue, right? Now, if I equate this summation formula with this 2 pi delta x minus 2 pi k going from minus infinity to plus infinity, right? I will use this formula for this equation, right? Then when I use this formula, I will get is 2 pi outside fx, and I have used the formula here. My formula was, this was my formula, x of minus 2 pi k. So 2 pi into delta x of minus 2 pi k. This is the value of the this term, e to the power I pi x. So this is the term. So minus sign will remain here with minus 2 pi, right? Now, so I get this minus 2 pi x minus 2 pi k dx, right? Now, from the property, from the property of this, what is this telling us? This is telling us a function multiplied by the delta function. Now, from the property of the delta function, we know that when a function is multiplied by the delta function, right? So from the property of the delta function, we know that the delta function is even. Delta function is an even function. It is whatever is on the left hand side of the y-axis or on the right hand side of the y-axis will be same, right? It's an even function. So we can treat these negative signs as positive. So I will treat these positive as positive signs. And also this is of the form of some constant times of the arguments or x plus k. So if you look at this delta function, what it is telling us, since I have assumed these negative signs as positive signs because it's an even function, then 2 pi will come outside. So it will be some constant multiplied by x plus k, right? So we can pull out 1 by 2 pi because it's 2 pi times everything. So if we put, now I can treat it like this: fx k going from minus infinity to plus infinity, delta of x plus k. So I can pull out the this term from here, right? So this 2 pi will cancel out. This 2 pi will cancel out if I pull out the 1 by 2 pi term from here. So 2 pi will cancel out, and I will be left with integral going from minus infinity to infinity, fx k going from minus infinity to plus infinity, delta x plus k. Now we are basically reducing this integral over the, now what is this integral? This integral is the summation of the delta functions to a sum over all the points. That is, when we are integrating, we are just effectively picking countable number of points over integral. So actually delta function multiplied by a function will actually be the function itself over these limits, over k going from minus infinity to infinity. Because if the delta function is delta function, what is delta function? Delta function tells us at certain points it will be, the value is 1. So therefore at these values of k it will be 1. So these values are multiplied with fx, it will actually result into fk at those points only. So hence this will be proved as k equal to minus infinity to plus infinity. This will be equal to the summation of the function. So that's what the point was. That's what the Poisson sum formula states that. It states that the summation of the function is equal to the summation of its Fourier transform. So I started with this equation. I'm using some renowned formulas which can be easily proved also. I will give you the proofs also. There's no, like I have I have used these formulas here. So I have started to prove this summation formula. I started with Fourier transform and then interchanging the sum and integral, right? Summation, after interchanging the summation and integral, I can say it is 2 pi because this is what the formula is. E to the power pi x will be e to the power I pi x will be equal to 2 pi. So 2 pi, when I replace this thing with this term, what I will get is 2 pi, because 2 pi will go outside, minus 2 pi x minus 2 pi k. So therefore, I say that it is 2 pi is basically, since delta function is an even function, I can change these negative signs as positive signs, right? So so 2 pi taken out, it will be x plus k. Now, if you solve that, it will be 1 over 2 pi of this function. So 1 over 2 pi will be cancelled with this 2 pi, and I will be left with this. So once you are left with this function, you can say when function is multiplied by a delta function, right? It's a countable points only. At those countable points, the function will exist. So it will be the summation of the function. So hence it proves that the Poisson sum formula, which states that the summation of a function is actually equal to the summation of its Fourier transform. That's the basic idea about the Poisson sum formula. Now we have already done with the Poisson Poisson distribution, but let us once again look at what are Poisson points basically. Poisson point process. Now it is a random mathematical object that consists of a randomly located points on a mathematical space. If you remember, last time I did an example in which the example was going like this. On an average, a restaurant is expecting 2 customers per 3 minutes, right? So with the passage of 3 minutes, 2 customers will come. So that is my first Poisson point. And when the next 3 minutes will complete, it will be the 6-minute reference. In that case, I will get 4 customers on an average, right? Whatever is the stated average. So that is my second Poisson point. And then 9 minutes, and I will get 6 customers. That is my third Poisson point. So it will be a random mathematical object that consists of a randomly located points on a mathematical space. So we can model the Poisson process as a mathematical on a mathematical space like this. The Poisson point process is often called the Poisson process. For example, this is my first point. After lambda interval, my second point happens. This is my 0th point. This is my first point. After lambda interval, again, my second point happens, and so on. And then let's say kth point happens. So this is a point. These are Poisson points after lambda intervals. Now, a visual depiction of Poisson point process scaling from 0, in which increments occur continuously and independently at rate lambda. So that's what this diagram is telling me. Now, if a collection of random points, including Euclidean space. Now, what is an Euclidean space? Euclidean space can be of 1 dimension, 2 dimension, 3 dimension, 4 dimension, and n dimension. If you talk about a 3-dimension Euclidean space, what it will look like, the normal Cartesian coordinate system, x, y, z. So every point can be expressed with 3 coordinates. A point in a 3D Euclidean space can be located by 3 coordinates. So you know how to find out the distance between the points. So this is a normal geometrical mathematical space, which we call as the Euclidean space. Now, if a collection of random points in Euclidean space forms a Poisson process, now these are the points as I have described. If these points form a Poisson process, I have already discussed what is a Poisson process. After regular intervals, you are there is an event happening, right? Then the number of points in region of finite size. So what we have got? We have got here the number of points, right? In the case of a restaurant, in 3 minutes, 2 customers will come. That's my first point. After lambda interval, 3 minutes will pass, which is my equal to lambda. So 2 more customers will come. So that is my second Poisson point. So in third interval, what will happen? Lambda interval will pass and 2 more customers will come. That's my third Poisson point. In the same way, I will have Poisson points distributed on a mathematical object, which we call as the Euclidean space. All right. So that's what I'm trying to say here. Then the number of points in a region of finite size. Now, these points will form what we call as a Poisson random variable, right? Poisson random variable. Then the number of points in a region of finite size is a random variable with the Poisson distribution. What was Poisson distribution? That we have already done one numerical also, and I have stated the definition and the formula for the Poisson distribution. Now, again, I am repeating the same thing. The Poisson distribution is the probability distribution of a random variable n called a Poisson random variable, such that the probability that capital N, this random variable capital N, equals some m, small n, and this probability is given by probability capital N is equal to this random variable capital N is equal to small n, is given by lambda raised to the power n e to the power minus lambda n factorial. Lambda determines the shape of the distribution, which is the regular period after which the next Poisson point will happen. Now, if a Poisson point process has lambda, right, of this form, where lambda is given by nu a, where nu is the Lebesgue measure, it assigns length area. So it's some measure. Let's not go into the details of what is this measure. If it is this kind of relationship between the if it is this kind of relationship that the regular interval has, And this nu is equal to Lebesgue measure, and it basically it represents the length, area, or volume to sets. It assigns length, area, or volume to sets. If it is a one-dimensional case, it will assign length. If it is a two-dimensional case, it will assign area. If it is a three-dimensional case, it will assign volume, and so on. And A is a constant. Then the Poisson point process is called homogeneous or stationary point process. If your regular interval, if the interval of the Poisson distribution, lambda is equal to mu A. So that's how we can define what we call as the Poisson points. That's very important to understand. What is a Poisson point? What is a Poisson process? What is a Poisson random variable? Right? So this you must understand. And we have already saw in my in the tute sheet number 5, I have given some questions on Poisson distribution. So you can just try to solve the question. And I took one example also in my last lecture. Right. So what we have done till now is the Poisson summation formula. We have discussed about what are Poisson points and the distribution. Now I will start with a new topic, right? I will give you the syllabus of the first evaluation, which will happen in the 7th week, 7th or 8th week, I don't know. First 6 weeks are your, no, 8th week it will happen. First 6 weeks will be your teaching, then 7th is your reading week. This is the 5th week ending, right? So one more week will come, then you will have a reading week. And after that, your first evaluation, which is multiple choice question or objective type questions, will happen from the syllabus that I will tell you, because I have to discuss about the syllabus. Today, I am holding a meeting with other faculty members that what is the syllabus we have to put in the exam. All right. So let us try to, I will not go into the mathematical concepts of Markov chain. That probably I will go in the next lecture. But I want to do one example, one very good example, where you will try to understand what actually are Markov chains and what is happening. What is a Markov chain? How a Markov chain helps in improving the system. Right. So let's look at this example. Very interesting example. I hope you will enjoy this. Suppose that an apple juice company, so there is some company which is selling apple juices, right, controls 20% of the apple juice market. So there is a company, so there can be many brands of apple juices, but this company, which we call as brand A, this company, covers 20% of the apple juice market, maybe Tropicana or Real. So let's not call Tropicana and Real specifically. Let's say brand A. It controls 20% of the apple juice market. Now the company wants to do an aggressive advertisement campaign, right? And for this purpose, they hire a research company. They want to go for a branding and advertisement kind of concepts. So they hire a research company to do some research that if we do this advertisement campaign, how it will affect the salability of the brand, whether it will improve or it will stay as it is, or it may decrease also with the ad. Right. So research company to predict the effects of the advertisement. Now, suppose this research company concludes that someone who is already using brand A will stay with brand A with 90% probability. So the company concludes that out of this 20% share, if somebody is using brand A, it will stick to brand A only. And that probability is 90%. So there is a chance, 10% chance or 0.1 probability that the people who were using brand A will not use brand A after this, and that probability is quite low as compared to the other probability, and that probability is 0.1, but there is certainly a probability. All right. And the second conclusion they see is that someone who was not using brand A out of, this second point conclusion does not fall in the 20% of the market. So it falls in the 80% of the market. So someone who is not using brand A, after this advertisement campaign, will switch to brand A. That's the advantage that we are looking for advertisement. You know, someone who is not using brand A should start using the brand with, and that probability they estimate it to is to be 70%, right? So 30% of the probability is that the people who are not using brand A, who are liking some other brand, will continue liking the other brand, not brand A. So that's the given scenario, right? So we want to know the effect of this advertisement campaign. So let us, and this we want to study through what we call as the Markov chains. And we assume that the people buy apple juice once a week. Once a week, people buy apple juice, and we will study the effect of the advertisement campaign on weekly basis, right? And so I will, since I have to work with the probabilities, so I will use some denotions. I will denote the brand A, the people who are using brand A or brand A usage with capital A, and some other brand usage with capital A prime. Right. So A prime tells me somebody not using brand A, and A tells me the usage of the brand A. Now I can make a state diagram here. I can make a transition diagram. So I will take two nodes. One is A and A dash. What does A tell me? People who are using brand A before the ad. A prime is people who are not using brand A before the advertisement. And what is this? A is the, okay. All right. So after the, I will come to the state diagram. I will come to the state transition matrix afterwards, but I just want to explain this transition diagram. So there are two states. The states are one who are using brand A, the other who are using not brand A, right? So after the campaign, after 1 week, let's say, what is the probabilities that these such companies have come out? So 90% of the people who are already using brand A will use brand A. So this probability that if earlier brand A was used, so the next state is brand A only. I mean, people who are using brand A, they will continue using the brand A, and that probability is 0.9. But there is a 0.1 probability that people who are using brand A will switch to some other brand, which is A prime. So that probability is 0.1. Second thing is that people who are not using brand A, that means A prime, will switch to brand A with 70% probability. So A prime is not brand A. So after the 1 week ad campaign, 70% probability is that they will start using the brand A. So it's a 0.7 probability. And 0.3 probability is that they will continue using not brand A. So this type of expression in the form of a diagram is known as the transition diagram, to illustrate when you are staying in your original state or changing states. So this is a relationship between the previous state and the next state. And this diagram is known as the transition diagram. All right, and we can express the same thing in the form of matrices also. And when I express the same probabilities in the form of matrices, and that matrix will be called as the probability transition matrix. And what is that probability transition matrix? Let's say I represent it with capital P. How can I make this matrix? Along the horizontal, along the vertical direction, these are the current states. It can be A or A prime. Along the horizontal side, these are the next states, and these will be A and A prime. Now, if the current state is A, that means brand A, it will continue with brand A, and that probability is 0.9. Earlier, it was brand A, but it will switch to brand A dash, A prime, its probability is 0.1. Same probabilities, but expressed in the form of a matrix. And somebody who is using A prime will use brand A with 70% probability. Somebody who was not using brand A will continue with some other brand with probability 0.3. And this when the probabilities are expressed in this form, in a matrix form, this is known as the probability transition matrix. Along the vertical side represents the current state, along the horizontal side represents the next state. And there is one more matrix, which is S0, current. This is known as initial state distribution matrix. Initial state market share, basically it is representing for our example. What is the market share for brand A? Initially, it was 0.2. Not brand A, it was 0.8. If you read this statement, you will see that 20% of the apple juice market was controlled by brand A. So that's what is written in the form of initial state distribution matrix. And these are the probability transition. This is probability transition matrix. This is the initial state distribution matrix. I can draw a tree diagram also from this example. What is my tree diagram? Initially, 0.2% of the probability brand A was there, 0.8 probability A dash was there. After the ad campaign, so people who are using brand A will 0.9 will continue with brand A and 0.1 will continue with brand A dash. People who are using A dash, 0.7 probability they will continue with A, they will switch to A, and 0.3 probability they will continue with A dash. So that's the different forms of expression of the probability, right? Now, probability that someone use after 1 week, what we want to know? We want to know what is the probability that brand A will be used after 1 week. So that means brand A, we can use the multiplication principle here. So this I will make, I will select 0.2. If you, mark the branches leading to A, right? So this, my first branch is leading to A. This 0.9 is also leading to A. Then in this direction, 0.8 is there. Then this 0.7 is leading to A. That's what I am crisscrossing, a crisscross line using 0.2, 0.9, 0.8, 0.7. If I use the multiplication principle, I will get what? 0.2 multiplied by 0.9, 0.8 multiplied by 0.7. 0.2 multiplied by 0.9, 0.8 multiplied by 0.7. This is multiplication rule of probability. And this comes out to be 0.74. This tells me that after 1 week of this advertisement campaign, and if this probability transition matrix is true, which they found that 90% of the people who are using brand A will continue with brand A and 10% will switch to brand A dash. But this is the key point. People who are using some other brand, 70% of the probability was there that they will switch to brand A. Right? So if this probability transition matrix is true, then after 1 week, what is the probability that the people will use brand A? It is 74%. It has jumped from 20% to 74%. 74% of the market will be captured by brand A. Right? Okay. So let's continue a little further. I will write this I denoted this initial state distribution matrix. I denoted it with S0, where the market share was 0.2 and not brand A was 0.8. But now after 1 week, this has changed. So the state distribution matrix will also change. And I will represent that state distribution matrix as S1. How I will write it? A 0.74, A dash 0.26. First state run. Earlier was 0th state matrix. Now this is first state matrix. I can find the state S1 also by this way. I can multiply S0 with P, which is the probability distribution matrix. What is my S0? 0.2 and 0.8. And what is my P, which is probability transition matrix? 0.9, 0.1, 0.7, 0.3. What answer I will get after this matrix multiplication? I will get 0.74 and 0.26. This I got from using the multiplication principle. And here I have used the multiplication of the initial state with probability transition matrix to get the next state. Right. Now, if I want, after 2 weeks, if I want to find out the effect of this ad campaign, and I use the same probability transition matrix, but I will use this S1. So it will be, what is my S2 in that case? S1 multiplied by probability transition matrix, which comes out to be 0.848, 0.152. So after the second week, the rise will not be that effective. So 85% of the market will be captured by brand A. After 3 weeks also we can find out, right? So in that case, my S3 will be calculated how? It will be calculated by S2 multiplied by P. In this example, I'm assuming a lot of things, right? The probability transition matrix remains the same. The findings of the research team are correct. But as an example, I'm trying to tell you what is Markov chain. So this is my Markov chain. After 1 week, after 2 weeks, after 3 weeks, I'm applying the Markov chain process. I am modeling this Markov process to predict the effect of a certain ad campaign in the coming weeks. So after 3 weeks, how the updation will happen in the state transition matrix? Since 85% here, 0.848, 0.15. So with multiplication of the same probability transition. So that will come out to be near 86%. So not a very large improvement is there after, as this was true for the case of when 1 week was elapsed. This is the introduction to Markov chains. Now this can be put mathematically. I will explain you how to put the things mathematically. In the next class, I will take the same example once again, and I will try to explain the Markov chains in a more formal process. But this is the effect. This is the introduction to Markov chains with the help of an example. That by defining a probability transition matrix, how the states are changing, how the Markov chain is formed, where the previous states are being transformed into next states, and then next states become the present state, and how you are getting the next state using those present states, and so on. And this process can continue. This is known as Markov chain, and this is known as Markov process to predict the effect. Right. And Markov chains have huge advantages in the subject of electronics and communication engineering, same as with computer science and engineering. So please remember that these are some very basic concepts, because these are the Markov process is the process which you can transform, which you can map to a recurrent neural net, RNN. If you might have understood, if you might have learned about the machine learning concepts, you must have come across with the CNN, convolutional neural network, or RNN, recurrent neural network. Now, recurrent neural network is basically a modeling of the Markov process, right, where the predictions can be done. But anyway, I'm not just trying to tell you the importance of this course, though it is a bit dry and a mathematical course, but the maths part is very important so that you can understand the concepts of, because when you writing a program is not that difficult. The understanding of the concept and the algorithm, and then how the algorithm is being applied, that's the important. That is the engineer's job or the designer's job. Anyway, if any questions are there, then please ask the questions. Otherwise, I would like to end the lecture, and we can continue the next class. If any questions are there, then. No? Anyway, thank you very much for joining with me. Thank you.